Okay, to continue with our discussion on random processes, we now discuss a set of very important processes, namely Gaussian random processes. Right? If you recollect, we have introduced the concept of Gaussian random variable earlier, and yesterday I talked about a set of random variables xi's to be jointly Gaussian. We say that a set of random variables x1 to xn are jointly Gaussian. This is a definition. If they are such that any linear combination of these, like this here, any linear combination of this happens to be a Gaussian random variable, right. So, if there are a set of n random variables x1 to x sub n, if I take any arbitrary linear combination of these resulting in a random variable y, and y turns out to be Gaussian for every such linear combination, then we say that xi's are jointly Gaussian, right. This is a definition of jointly Gaussian random processes. So, now this will, is that okay? Y is Gaussian, this is Gaussian. We can now extend this definition to define a Gaussian process. Incidentally, before I do that, let me also mention that in this particular case, the joint distribution of x1, x2, x3, right, there will be a joint distribution of these, would have a form, would have a specific form which is called jointly Gaussian density function, right. So, when they are jointly Gaussian, there is also an associated density function, which is of course very easy to generate if they were statistically independent, but in general they may not even, these xi's need not be statistically independent for this definition to be valid. Okay. So, what the density function is something that I will discuss a few minutes later, but there is an associated joint Gaussian density function of these n random variables. Okay. We will see the form of that joint density function in a few minutes. So, we say that a random process xt is Gaussian or a noise process x of t is Gaussian by essentially generalizing this definition, right. If you have a random process xt rather than discrete values xi, these are, you can think of I as a discrete index going from 1 to n and t as a continuous index, right. So, how will you generalize this? Essentially in integration, and with g sub I replaced with some function g of t, right. So, I generalize this and that gives me the definition of a Gaussian random process. So, we say x of t is Gaussian if every y that you construct like this, or 0 to t or minus infinity to plus infinity, it does not really matter, that depends on the domain of t. If y defined like this, which is essentially, once again you can think of x of t denoting different random variables, except that it is an infinite set of random variables going from going over the domain of t, right, and g of t is a corresponding multiplication weighting coefficient, right, and you are summing up all these weighted random variables exactly in the same way that you are doing in this case, right. So, if this is a Gaussian random variable, so once again you have generated a Gaussian, once again you generated a variable here, it is not a function of time, time will disappear in this, right. So, you are taking a linear combination of these random variables and generating a random variable here. If this happens to be a Gaussian random variable, we say that the process xt is Gaussian, right. For if this is so, for every choice of the combining function g of t, right, these are the weighting, this is a weighting function or the combining function, with the constraint that this function should satisfy this condition, right. If this is true for every such GT which is a finite energy function, right, if y happens to be a Gaussian random variable, then we say that process xt is Gaussian. Okay. Now, Gaussian random variables, as I mentioned some time ago, and Gaussian processes, they are very commonly used models for physical phenomena. If you recollect, I mentioned this earlier, and the reason and the justification for this use is a result from statistics and probability theory, which is the central limit theorem. I will just briefly mention this for the sake of completeness. Right. The central limit theorem provides the mathematical justification for using a Gaussian process model for many physical phenomena, right. So, let me state what this theorem is. Let x sub I be statistically independent identical random variables. Right. By identical random variables, I mean identical PDFs. They have identical, that is, they have identical density functions. That means it does not mean that they are the same random variable, right? They are different random variables, identical PDFs. And let us say the ith random variable has each of them has a mean equal to mu sub x and variance equal to sigma x square, right. Let me define a random variable y sub I, which is 1 by sigma x. This is a normalized random variable essentially, x I minus mu x, like that, I going from 1 to n. So, from the ith x I have generated a y I. How is this y I different from this x I? It is normalized to have 0 mean and unit variance, right. So, basically that is the purpose of defining these normalized random variables. So, this normalization would imply that the average value of this is 0 and variance of y I is equal to 1. Let me further define a random variable v sub n, which is obtained by taking the sample average or taking the average of these n random variables, not exactly average, because I am not going to divide it by n, because I am going to divide it by root of n. It is not really average. So, just adding up these and dividing it by root of n, right. This division by root of n is again a kind of normalization, okay, more than anything else, right. Then the central limit theorem states, this is the most basic version of the central limit theorem. There are more advanced versions of this which will generalize these results. The most basic version of the central limit theorem states that as n approaches infinity, the random variable v sub n will tend to become a normal random variable, again with 0 mean and unit variance. Okay. So, that is the statement of the central limit theorem. The central limit theorem states that V n approaches a Gaussian random variable with PDF becoming normal with 0 mean and unit variance as n tends to infinity. Okay. So, please note that initially I have not put any kind of, I have not said what distribution x i's could have. They could have any distribution, they need not be normal at all, they need not be Gaussian at all, but if I add a large number of such random variables which may not even be Gaussian themselves, right, the result is a Gaussian random variable. That is the central limit theorem. It is not difficult to physically or intuitively see why this should be so, right, because you already have some idea of these things, but in case you do not have, let me just give you a physical picture for this, why this should happen. Suppose I have two random variables x1 and x2 and I add them up. This is just to physics, I am not doing a very strict proving here, just giving you a physical feel for why this result should hold, right. Suppose I have two random variables x1 and x2 and I generate a random variable y which is the sum of these two. Let us say x1 and x2 are both uniformly distributed random variables, both of them have uniform PDF, right, nowhere near the Gaussian PDF, totally different from it. Now, do you know what will be the density function of y? Suppose x1 and x2 are statistically independent and I ask you what is the density function of y, would you be able to say something? Okay, maybe not. I will leave that as an exercise for you to prove. This is, consider this as an additional problem in the problem sheet that I have given to you. Exercise is to prove that Py, the density function of y, if x1 and x2 are statistically independent, would be Px1x convolved with itself, or Px2x convolved with Px2x. That is the reason, I mean that is something very simple to prove by just very elementary considerations of the definition of density function and things like that, right. So, let us start with this, assume this result is okay, which is very easy to prove, and based on this we can argue why the central limit theorem should hold. So, as I said, assume that both x1 and x2 have uniform PDF, then what will be the distribution function of y? Uniform means they are rectangular functions. You convolve to rectangular functions, what do you get? You will get a triangular function. So, you start with things like this, right, this convolve with this will lead to this, right. Now, let us say I add two more such random variables to obtain y. So, let us say y is now defined as x1 plus x2 plus x3 plus x4, all uniformly distributed, right. The sum of these two has a triangular distribution, right. The sum of these two again has a triangular distribution and you are convolving these two. What will you get now? You will get a parabolic function, right. So, already you see that the resulting function is starting to resemble a Gaussian shape, right, is not it? So, and as you add more and more such random variables, this tendency to become normal will become bigger and bigger. So, that intuitively gives you a picture as to where does this result come from. It basically is a result of this most basic probability theory result, which is very easy to prove, and I am giving that as an exercise for you to prove. These are given in most books, or you can also prove it yourself. So, that is the reason why Gaussian processes are used as models, because it turns out that many physical phenomena indeed can be expressed as sum total of a large number of micro phenomena, and that is what you really observe. You observe the macro phenomena and not the micro phenomena, right. The micro phenomena may not be Gaussian in nature, but the macro phenomenon that you are observing will turn out to be Gaussian in nature, right. Now, since Gaussian processes are very important, let us study a few important characterizations or properties of Gaussian process. So, let me talk about some properties of a Gaussian process. Now let me ask this question. Suppose I pass a Gaussian random process through a linear filter. Okay. What kind of process will I get at the output? Can you say something? What will be the nature of the process at the output of the filter? I am not asking you to find the autocorrelation function and anything else. Can you make any generic statement, any general statement about the nature of the output process? Okay, let me make the question more focused. Will it remain Gaussian? Yeah. How does it follow? Linear. It follows from the definition of the Gaussian process, more or less. How do I define a Gaussian process? Right? Just think about it. I define a Gaussian process xt to be so such that every linear functional which is integral of gt xt dt, that turns out to be a Gaussian random variable, and that convolution relation that holds is essentially that kind of a relationship for every time instant. So, at every time instant you are generating a Gaussian random variable. If you are generating a Gaussian random variable at every time instant, this will have the same properties, right. So, it is, of course, this is not a detailed proof, it just gives you an idea of how to argue this out, but a detailed proof is available in the book. I would like you to read it yourself. So, if xt is passed through a stable linear filter, then the output process yt is also Gaussian. So, this is a very interesting and useful property of a Gaussian process. So, Gaussian processes are not only something that we can expect to occur naturally, to be found in nature extensively, but also they have some very convenient properties in terms of their mathematical properties, which are therefore useful when you are working with mathematical models. A mathematical model should be easy to work with, and it turns out that this has some very nice properties which makes it very easy to work with. So, the proof leaving as an exercise. Okay, at this stage let me come to that question which I raised some time ago about how do you characterize the density function of the process, of a Gaussian process, right. Well, that is equivalent to asking how do you characterize the density function of n variables which are jointly Gaussian, isn't it? And that is the issue that we are, because ultimately how do you characterize the density function of a process? You sample the process, generate n random variables and try to give the joint density function of these n random variables. That is the most general characterization of any random process. If you can do that for every value of n, for every choice of the sampling instance, then you have a complete description, right. So, for a Gaussian process, so instead of talking about a Gaussian process, it is really more important to talk about n Gaussian random variables, n jointly Gaussian random variables. How do you characterize their density function? All right. Let me start with a very simple physical picture. Let us say x1 to xn are n Gaussian random variables which are also statistically independent. In general they may not be, as I mentioned earlier. Assumes they are statistically independent to start with, only to start with. We will remove this assumption later. Okay, assumption of statistical independence will be removed later. Now, let me say that this is Gaussian or normal with mean mu x1, this has mean mu x2, etc. Right, and let us say the variance of this is sigma x1 square, this is sigma x2 square, and this is sigma, this should be x sub capital N xn square. Okay. Now, if I have to ask you to write down the joint density function of these n random variables, is it easy to do or not? What is it? It is simply the, so individually they are normal. So, what is the joint density function of n statistically independent normal random variables? It will be the product, isn't it? So, if I were to write the joint density function of these n random variables, that is going to be equal to the product of going from I to 1, I is equal to 1 to n of 1 by root 2 pi sigma x I e to the power minus x I minus mu x I whole square upon 2 sigma x I square, right. This is easy. So, if I have n jointly Gaussian but statistically independent Gaussian random variables, writing the joint density function is trivial. You just multiply them, right, because of the independence property. Now, what I want to do is remove this assumption, but before I do that, let me try to rewrite this expression in a manner which will help me to write the general expression, where I do not have to make that assumption. Okay. So, basically that is the attempt that I am going to do. To do that, let me define a few things. Let me define, I will have to use what is called a vector notation or matrix notation for writing this density function. Okay. Let me define, this is of course the definition already. Let me define a covariance between the ith and the jth random variables as x I minus mu x I, expected value of x I minus mu x I into x j minus mu x j, right. That is the definition of the covariance. Variance x I minus mu x I square, that is sigma x I square, right. And I define C x or C maybe sigma, this is a more commonly used definition, as a matrix whose ijth element is C x I j, right. So, if these n random variables are statistically independent, what is the nature of this matrix? The ijth element of sigma, this is matrix, this is just a notation for a matrix which I am calling sigma, right. What will be the ijth element is C x I j. What is the value of C x I j when these are independent? No, it is 0. This is a central moment, remember that. Yes, it is product, but each expectation itself is 0, isn't it? The first moment, first central moment is always 0. So, yes, this is equal to expected value of this into this, but each of those expected values is 0. So, this is 0, right, for I not equal to j. So, if I were to think of sigma as a matrix whose ijth element is given by this, what kind of a matrix is this? It is a diagonal matrix, right. Is it clear? What are the diagonal elements? The variances sigma x 1 square to sigma x n square. Let me drop this x here, it is not for serving any purpose, sigma 1 square to sigma n square, and all the other elements are 0, right. This matrix is defined to be the covariance matrix associated with the n random variables x 1, x 2 to x n. In fact, let us think of this collection of n random variables as a vector. You can represent a collection of n quantities as a vector, isn't it? Let me show this as a column vector. So, I have a column vector whose n components are the n random variables I am talking about, and the covariance matrix therefore represents the covariance between every pair of the components of this vector, right. The ijth pair would have a covariance which is this, and that is the ijth element of this. For statistically independent random variables, the covariance matrix would be diagonal. For random variables which are for vectors whose components are not statistically independent, this will not be a diagonal matrix, it will be a full fledged matrix with non-zero entries for all elements. Okay. But let us at the moment come back to this. We had this, we want to write this expression now in terms of these two entities. Can we do that? More precisely, let me ask you, look at this exponent. Okay, before we do that, I think we need to do one more step. I come back to this expression. This product I can take as a summation over these exponents, isn't it? I can write therefore the joint density function as 1 by, if I multiply root of 2 pi n times with itself, I will get 2 pi to the power n by 2, right. Similarly, sigma 1 to sigma n, right. So, this will be a product sigma 1, I am dropping the x here for simplicity of writing. This will be sigma 1 to sigma n, multiplying sigma 1 to sigma n, right. So, that is as far as the coefficient is concerned, this gets modified to this form. What about the exponent part? This becomes e to the power minus summation over I is equal to 1 to n of all these terms. Is that okay? Maybe I can take the half outside. Is that fine? I have just dropped the subscript x everywhere for convenience. You will grant this? So, basically this product here becomes this summation here. Now, try to imagine writing this summation in terms of a vector matrix product of some kind. Can you see, can you express this summation in terms of these quantities, this matrix sigma and this vector x? Okay, let me give you a hint. Consider this product. Let me denote this as a vector x, right. So, vector x is a column vector whose elements are x1 to xn, right. So, what will be x transpose? What kind of vector is this? A row vector, right, whose row elements are x1 to xn. Let me multiply that with sigma inverse. Consider this quantity x transpose sigma inverse x, right. This is equal to x1 to xn, right. Inverse of a diagonal matrix is very easy. What is it? All the diagonal elements will become, we will take the reciprocal of those, it will be 1 by sigma 1 square to 1 by sigma n square, zeros here, and what do you get here? x1 x2 to xn, right. Now, can you tell me what this product will be? This is actually what is called quadratic form of a matrix A. You know, things like x transpose Ax, where x is a vector, is called the quadratic form of A, and this actually can be written as a double summation Aij xi into xj. It is very easy to prove this. It's just you have to multiply these matrices. In fact, it is obvious what this will be. You won't even have a double summation because the diagonal element, only diagonal elements are non-zero. If you were to expand, you multiply this row vector with this matrix and this the resulting matrix with this column vector, actually you will get a scalar, isn't it? This is 1 into n, this is n into n, this is n into 1. What is the overall product like? It is a scalar 1 into 1, and the value of the scalar is 1 by sigma 1 square into x1 into x1 plus 1 by sigma 2 square, right. So, actually this term here is precisely this term, except that I am not multiplying with x1, but it should become x1 minus mu 1, this should become xn minus mu n. So, if I were to define the vector x minus mu as this vector x1 minus mu 1, x2 minus mu 2, etc. Now, you can see how to write that expression. Your joint Gaussian density function essentially becomes 1 by 2 pi to the power n by 2 sigma 1 sigma 2 sigma n, and you have e to the power minus x minus mu transpose sigma inverse into x minus mu. This sigma is not summation, this is a notation for the covariance matrix, and half here. No, that is taken care of by sigma to, isn't it?
Yes, sir.
That is precisely what sigma inverse is. Is that okay? Everyone? Please see. It just what we are saying is that this quantity is equal to this, except that I have not put the mu i's here, they are the same thing. So, I am defining x minus mu instead of x1. Instead of the vector x, I take the vector x minus mu here, the vector x minus mu here, and you get this, right. I can simplify this further. Can you express this product in terms of this matrix sigma? Remember what is sigma? Sigma is this matrix whose diagonal elements are sigma 1 square to sigma n square. So, can you identify sigma 1 into sigma 2 into sigma n as something relating to this matrix, some property of this matrix? It is nothing but the determinant, square root of the determinant of this matrix, right. So, I can write this as further as 1 by 2 pi in a more compact form to the power n
by 2, n by 2.
Yes, this should be n by 2, and this you can write as determinant of sigma square root of that into exponential minus half, etc. Right. So, here is a general expression. I hope you are with me. If I have n jointly Gaussian random variables, right, which are statistically independent, I can write that simple looking expression by a more complicated looking expression like this, right. And why should I do that? Why should I go into this vector matrix notation? Because now I can just generalize this for any set of random variables, whether they are independent or not, right, because the covariance matrix will capture the information about their statistical dependencies, right, and this becomes a special case. When sigma becomes diagonal, this becomes a special case. Okay. So, that is what you need to know. So, and even this joint density function I do not have to write like this, I use the vector notation and get a compact notation for that, p x x, just simply write that, it means this, right. I have vector x and I am writing the density function of this vector x, which essentially means the joint density function of its components. So, when I talk about the density function of a vector, what it really means is we are talking about the joint density function of its components. Is that clear? This is notation, nothing else. So, that is the most general form for the expression, the most general expression for the jointly Gaussian random variables. 2 pi to the power n by 2 determinant of sigma to the power half into exponential of minus half x minus mu transpose sigma inverse x minus mu. Okay. So, if I now give you a Gaussian process x t, can you characterize it? Yes, I can, because I know that if I choose some sampling instance t 1 to t n, any whether n is 1 or 2 or 3, right, there will be an associated set of random variables x 1 to x n, and what I need to know to write the corresponding density function is their mean values and their covariances. Right. If I have all that information, then I can write this density function, right, and the covariance information can be obtained from the autocorrelation function, isn't it? Because what is autocorrelation function? It is x t into x t plus tau, or x t 1 into x t 2, right. The covariance, the corresponding covariance information will be expected value of x t 1 minus mu 1 into x t 2 minus mu 2. So, if I know this and if I know the mean values, I know it. So, if I know the autocorrelation function, I can write the density function for any set of n random variables that I may encounter in a Gaussian process, or that I may generate from a Gaussian process. The information in the autocorrelation function is sufficient to write the complete density function, which is a manifestation of a fact which we earlier know, that a Gaussian random variable is completely characterized in terms of its first two moments. Similarly, a Gaussian process is completely characterized in terms of the mean value function and the autocorrelation function, because from these two informations I can generate all the information that is necessary in writing any density function of this kind, right. Are you all with me? Okay. I think that is sufficient information for a Gaussian process to start with. Let me wind up this discussion on random processes by just stating one last result about representation of narrowband Gaussian processes. Narrowband processes, random processes. Which is a straightforward extension of our understanding of representation of narrowband signals, narrowband deterministic signals, right. Do you remember what the result there was? How do you represent a narrowband signal? We had developed a quadrature representation, right. Every narrowband signal could be expressed in terms of two quadrature components which were low pass signals and the corresponding center frequency, right. So, this result can be, now this is an important issue to work excuse me, this is an important issue for us, because I mentioned earlier that most of the time the random signals that we will work with, which is essentially typically noise, right, will be wideband signals. We talk about white noise, which has very wide bandwidth, right, but it is not always that we work with wideband signals. Suppose the same white noise that is coming along with the signal is passed through a filter, let us say a narrowband filter, and your communication receivers are full of band filters, isn't it? Filters tuned to some frequency fc. Now, what will be the nature of the process noise at the output of this? It will not be any more wideband. It was wideband at the input, but at the output of the filter it will be narrowband noise. So, you need to invoke this representation there. So, just like we had for a deterministic signal a quadrature representation of the signal for when it was narrowband, we can have a similar quadrature representation for the narrowband noise. Right? That is, we can express x of t in terms of an in phase component x I t multiplied with cosine omega c t plus or minus a quadrature component x sub q t into sin omega c t, right, where x of t is your narrowband noise or narrowband random process, and x sub I and x sub q would be equivalent low pass processes. That is, the information about x of t is really contained in these two quadrature components. Is that okay? Of suitable bandwidth. It will be, maybe I should give you a couple of exercises in this connection. I would like you to show, for example, that you see, first of all, appreciate that this is a rapidly fluctuating process and these are slowly fluctuating processes. You can incidentally also write this in terms of envelope and phase. So, there is an envelope process, you know, r of t into cosine omega c t plus phi of t. You can also think of this as this, where phi of t would be tan inverse of x q upon x I and r of t would be
x I square plus
square root of x I square plus x q square. So, you can think of this as an envelope random process, a random process which describes the envelope of the narrowband signal, and this is the phase process which describes the instantaneous phase of the narrowband noise, right. Now, these are important representations, because when we discuss either amplitude modulation or phase modulation and the impact of noise on that, then it is obvious that this as well as this representation will be very useful. Now, a few things that I would like you to find out is, show that the average power of each of these three processes, namely the original narrowband signal and the quadrature representations, the two quadrature representations, they have the same average power, that is they have the same variance, right. So, please show that the variance of x t is equal to the variance of x I t is equal to the variance of x q t. Okay. Also, this is one property. The second property is, I think maybe for this property they would a scaling factor is involved, or you have to suitably modify this definition if required. Maybe a 1 by root 2 have to be involved. So, please check out and let me know whether this is fine or whether you need to multiply this with root 2 or something, right. Basically, this is there is a normalized representation, so that this result holds, right. If there is any scaling, please work it out and let me know. The second result is, if x t is a narrowband Gaussian process. So, I am not saying just narrowband, I am saying narrowband Gaussian process, right. If x t is Gaussian, then both x sub I and x sub q will also be Gaussian. Please work out an argument, suitable argument for this. Okay. And as a further special situation, if x t is 0 mean Gaussian, that is the mean value function is 0, then the quadrature components are statistically independent. Okay. So, these are some of the properties. Please learn the proof of these properties as well as other additional properties which I have not done here, which are available in the book. So, because of limited time, it is difficult for me to cover random processes exhaustively, but I think I have covered sufficiently exhaustively for us to now feel comfortable with it, provided you do enough problems from the book, right. And we are ready to use them now for as models that we need to use for modeling noise in communication systems and studying the effect of noise in communication systems. So, I will stop here and please review this quickly so that we can get on with the job. Thank you very much.